Good morning, everyone. Yeah, and I'm going to try to attempt again recording the lecture. So the different laptop today, as you can see, then I'll see how it goes. All right, today the session will start with solar, and unfortunately, we usually start with some sun outside. I can see the blinds are in, so we can not have that liberty. Is it better? Is it okay? You want to knock it off completely or want some light? That's good? Okay, guys, thank you. Okay, today's session is solar radiation. Before I start the session, anyone has any comments or suggestions or questions on the last class or on assignments? I'm happy to take, so I can hold it for another 5 minutes before I start the lecture. 5 or maybe 3-4 minutes. Any questions on assignments? And I should say that I'm really happy with your progress. You have done an extremely good job in selecting the topics. They're all the topics which you have selected so far has some uniqueness, and it's really good. It's really good. So it's really good to be good to read your stories, and some of them even gone for rainwater harvestation. I think it's Declan Ball. It's a good topic, actually. I should say it indirectly affects the renewable energy conservation, and some people have chosen solar, wind, hydro, thermal. So it's all good topics. So anyone have any questions, comments?
So I have been unable to access my wiki.
Come here. I want to fix it now because I don't have time after the class. I think I have sorted yours, right? You asked me.
Yeah, but I couldn't.
Sorry, lads, just 2 minutes. I think I did. Is it Robinson, right? Yeah. You want something bigger than this?
Yeah.
The screen.
Okay. Big, yeah.
I think I fixed yours.
You told me, but I told you
Same with you as well. Is there anyone having problem apart from these two? No. Okay. I think I fixed yours. I remember.
Yeah, you told me, but I told you
Right. Robinson, right? Who's down?
Yes.
What's your name? Anthony Mini, right? Antonio Amelo. Okay. So I think I put you to edit. What is your name? Gmail address? This is you, right?
Yeah, that's me. Yeah.
What you do? What's your name? Yours what this one, right? Yes. And your Gmail address is I saw your Gmail, right? US is also not there. I think the video is good. Okay, now you should be able to that's US, right? I don't know US is not. Is there a problem with this one? Oh, geez, no. I thought it's only one I got quickly here. What's your name?
Faraj.
Sorry?
Faraj.
Faraj. Okay, Faraj, I'll fix you as well. It's 15 minutes left, right? Okay, you should have been done. No, you could edit. You should be fine. See, it's there. That's you, right? Is it not a human audience? Okay. I do it again. I think wait for some more time. You can do it. You can go now. Okay, yours is?
No, I'm okay now.
You're okay now? Okay, right. Right, that's no more questions. We will start. Then I will be hanging on to this forever. Alright. Right. Lads, there is no solar in the class today, so no more photons. So I don't want to make you guys sleep. So I would like to be as more interactive as we can. Okay. So solar radiation today. So what do you think about the cartoon on the right? Do you think it's realistic? Who is going to do the project on this? Putting on the wind. The guy here mostly talking about the wind energy with the flags on, and on top solar cells. Can we do that?
Why is there smoke coming out of that?
Sorry?
Why is there smoke coming out of that?
Yeah, it's not happy with that. You killed my oil. So we are predicting a nice comfortable flight today, folks, unless of course we run into any cloud cover. Is that true? If you run into the cloud cover,
No.
yeah. Okay, we'll come back to this no, why, how. Let's start guessing, okay? So I want to put another cartoon to start with. This is what is going to happen. This is my prediction in few years. Of course, I took it from the, again I can reference this. So I suppose this means we should invest more in solar. Now you know the greenhouse. I think we have been talking this over the past 6 classes, the necessity of renewable energy. And and also in the first class we discussed about how much investment has been made between US, Europe, Asian countries are all. So there's a huge need, requirement, job opportunities, everything will be there around the renewable energies. And this is a classic example. Suppose we should invest more in solar. How? Well, it all depends on how we are going to do the assignments. How well, what is the best business model, all the story will figure out. Okay, that's as usual. Just a quick reminder before we start, please turn off your mobile. Okay, I think somebody didn't do last week. I think I noticed. I don't want to mention the name of guys, so it was slightly annoying. Right, let's do the overview. The overview, I'll start with solar energy, and I have clubbed these two together, solar irradiance and characteristics, into one topic. And I would be touching on angle of incidence, geometrical parameters. So angle of incidence, as you may aware, we have been discussing again that how the angle of incidence is going to affect the energy storage and also energy transmission. I think we just briefly discussed a few classes back. I think in the first class, I think, if I'm right. And effect of atmosphere. Are you able to get what does that mean? Effect of atmosphere. Come on, go on.
Well, obviously, in the atmosphere, some of the solar is reflected back in space. So depending on the atmosphere, it depends on what solar actually goes down on the Earth's surface.
Okay. Yes and no. So you're superficially touching the status. If you go back to, I think you can do better. Seriously, you can do much more better. Having come to the classes, you have been there for all classes, right? Yeah. Don't think that way. Yes, you can do really better. Think about that a bit more. Okay, we come to the class. Then we are going. Then you can answer it very clearly. Any more? Effect of atmosphere. What does it mean? One killer wave. One killer answer I'm looking for. One killer answer. I will even give you the killer answer clue. Fact of life. Guys, fact of life. Don't tell me the fact of life is out gone. Do you remember this fact of life by any chance? Yeah, exactly. How we are going to do it effectively? That is solar. It's the heat energy, right? Converting it to work to heat. So how effectively we are going to increase the efficiency by different technologies? That is key. And how the atmosphere is influencing this. As you mentioned, the reflection, absorption, latent heat. I will all come to it. Latent heat, specific heat that will play, and also the angle of incidence and geometrical parameters. Can you comment on that as well? Angle of incidence and geometrical parameters. You know the answer, guys? Sorry?
The sun is moving. You want to harness it, so you want to capture it. So you want to make sure that the angle of incidence is always perfect to the sun at all times. So you have some most of the energy from the sun.
Fantastic. I can take that. I'm looking at the broader picture. Broader picture. Compare. I think the topic of your assignments is also something similar, right? Compare Ireland with respect to the rest of the world. Is that correct? How we are going to do that? Is there anything can you relate with respect to angle of incidence, geometrical parameters, how well Ireland is placed, blah blah blah? Sorry?
Do with the position of the globe.
Globe, exactly. That is what geometrical parameters will dictate. What is the latitude and the longitude, and then what position you will get the sun, if at all you get sun. So how many hours will the cloud influence there? That's again boiled down to effect of atmosphere. Okay, I will also touch down the key parameters for consideration. So before I do, I want to go for make something life interesting. When I see something interesting, I don't even find any chalk here. So that's that really. Okay, what are the key parameters you think for consideration? We'll touch this point towards the end of the class, but I just want to get your highlights on before then we can see whether we are going in the right direction or not. Key parameters.
Key parameters of solar radiation.
Of course.
It's going to be time of year and time of day.
Time of year, time duration.
Yeah.
Okay, that's time. Another one.
Exposure.
Sorry? Exposure. Okay, exposure, time. Sorry? Cloud cover. Okay, that's exposure and cloud cover. Both I can marry together.
Local geography.
Sorry?
Local geography.
Local geography. Okay, local geography, time, exposure, cloud cover. Some more. Don't tell quantum computing, okay? Solar panel efficiency. Okay, solar panel efficiency. I'm just going for words, that's it. Some more. Don't Google it, okay? Don't Google it.
Radiation absorption,
Okay, that's the effect of atmosphere, radiation absorption, okay? I agree with that. That also comes under this. Is that what you meant?
Yeah.
Okay. Yeah, that's directly affects the panel, right? You're talking about material properties. Is that correct?
Yeah.
That's fine. Now I'm looking at the broader picture. Broader picture in the sense the key parameters like this, as you said, absorption, things. We don't touch material properties. We talk about renewable energy and technology, what technology needs. So I got 5 points. You'll see that these 5 points will choose. One more. Any one of the volunteers?
Financial considerations, investment.
Right. Government policies.
Yeah.
Okay. Government policies. He's hitting the nail. Awareness. Okay. I don't know whether that's in my slide, but I've definitely included that in my slide. If it is not. Any more? Again, the right line one I got, so I haven't got one from there. That's fine. I think I asked more questions to the guy here. That's why he's missing. Yeah. Any more? Okay, guys. I think I'm wasting my time. Okay, let's move on. Energy from the sun. Energy from the sun. Renewable energy converts energy. Renewable energy systems converts energy, and the main source for that is sun. That is solar. How much energy does the sun produce? How much energy does the sun produce? Can you tell me how much energy does the sun produce every second, and then every hour? Any guesses? It's a wild guess. I don't want you to be accurate. Wild guess. How much energy will it produce? I think you have 1 second. You have to be very clear. Sorry to break you. The unit. What is the unit first? Because we talked about units the first class. Joules. So tell me in joules or in power watt, whichever is convenient to you. Make a wild guess.
What about what's it? 1,000 watts per square meter?
1,000 watts per square meter.
Yeah.
Okay. 1,000 watts per square meter. Do you think that that's the thing which energy is producing? Okay, I'll take it. Any more? You said 20,000, right?
No, I said 1,000 million joules.
1,000 million joules.
Yeah.
Okay. 1,000 million joules per second.
No.
Per hour. So you're talking in watt hours.
Yes.
Okay. I like these guys. They are discussing a lot. Brainstorming session already going on, guys. Come on. If you are put in sunlight, that's it. It's going to burst. Any more?
10 gigawatt per second.
10 gigawatt per second. Are you into software? Gigahertz, gigawatt. It's 3.8 into 10 power 26 joules per second, okay? So 3.8 10 power 26 watts hours. That's what the amount of energy per second. So calculate in 1 hour by yourself. Okay, you know what it is, 3,600 seconds in an hour, okay? How much energy is produced? How the energy is produced from the sun? This is an interesting question. How the energy from the sun is produced?
Well, it's a huge ball of fire.
Okay, before I this guy is a terrorist. Huge ball of fire. Okay, I agree with you. Huge ball of fire. Fantastic. But how the fire is produced? That's my question. Okay, right. How many of you are physicists? This is a killer way for physicists. If they are telling it, I'm going to kill them. Guys, I saw four people. Nobody there today, is it? Don't tell me that. Sorry? Are you physicists, right? Yeah, look at that. Raise your hand right away, straight away. Okay, you are into trouble now today if you are not answering this. Okay, you are a physicist as well, right? No, I'll take you as a physicist. Today you are wearing the hat. Get in.
What?
No, somebody was saying it. Okay. How the energy is from the sun produced?
Nuclear fission.
Nuclear?
Fission.
Fission.
Yeah.
Do you say fission?
Yeah.
Okay, how fission?
Because the atom split produced energy. It's not done.
Which atom is splitting?
I just know it's called nuclear fission because fusion is what we do, and that's not fission. That's the opposite of what the sun does. That's all I know. I know nuclear
Okay.
power is nuclear fusion. the sun is nuclear fission. That's because we get to nuclear fission because it's more efficient than nuclear fusion.
I think you're better off with engineering. my word is going against you now. No harm done, okay? Any more? Fusion. How fusion? See? Opposite directions. Exactly, dynamically opposite. How fusion?
It's usually the hydrogen atoms.
Hydrogen atoms and?
In the sun, because plastic is better.
Hydrogen atoms. So you mean to say two hydrogen atoms fusing together. Do you think? What is that inside the sun? That's a question I need to ask you first. Because that is the source of solar, right? That is the source of all renewable energies. What is that inside the sun? Then that question you will answer.
Heavy metals?
Heavy metals? Heavy metals. I'll come back to you.
Hydrogen and helium.
Hydrogen and helium. Okay. Okay. That's it. Okay. Hydrogen and helium. That is the major part. Now you tell me. You said fusion. Anyone? Sorry? Ah, yeah. No. I'll give you the answer. Don't worry. I'm not leaving you without answer. Anyone? Okay, guys. You have been watching all these Iran-Iraq wars and killing of Gaddafi, everything. Now you tell me how energy is produced in the sun. What is happening there? Why people are going opposing nuclear bomb? What is happening there? How hydrogen bomb is produced? Don't tell me. I'm not giving you a class for terrorism here. Okay, I'm trying to get an answer. I go with him, but I want more constructive answer. I want to put the things together.
Splitting atoms.
Splitting atoms. That is fission he's talking about, is it?
Is it a collision?
Collision.
Collision of atoms.
Collision of atoms. What atoms?
The atmospheric.
What atoms? No atmospheric, no nothing. I want the name. Helium and hydrogen collision.
Yeah.
Okay. Okay. It's all more hand waving. It's called thermonuclear explosions. Okay? Thermonuclear explosions. And I will go with you, hydrogen, helium, you, fusion. And after that you corrected actually when I said, okay, it's like hydrogen and helium. When you bring these two together, it needs huge energy that is being released. Right? That energy is the source for the solar. The fusion of the sun. And I will have more specific examples to give so that makes these explosions fuse atoms of hydrogen into the atoms of helium. That's why it is responsible, and that's why the majority is causing this explosion. Okay? Energy. A tremendous amount of energy is released during the thermonuclear reaction, and the sun realizes that energy as radiation. That's what is radiating out. This fusion. That's why people here are very concerned about nuclear is fused. Plenty of energy is released, and this energy is really harmful. It can destroy everything. Right? What happened to Japan? It's a nuclear bomb. It's a fusion again. That's released and destroyed everything. Okay, so that's a fusion. And I will also talk about this at some stage. Can you give me some more example? Okay, I'll give you this. This is what happened. Thermonuclear. So this is courtesy NASA. So it's a cartoon picture of sun releasing the energies towards a star. Ignites. This is like a, what is that? Supernova. That's the name. Supernova. So thermonuclear expansion as it ignites and spreads and then helps the entire neutron star. Okay, that's one of the example of thermonuclear reaction. And then the right is the detonation of 11 megaton nuclear reactor bomb. That's again a fusion of hydrogen. Okay, and that happened in the Republic of Marshall Islands. Okay, that's a classic example. I just want to give you a flavor of how much impact that energy is causing. This is only about 2% of the energy released, or less than 2% what sun has got. Okay, imagine it's a huge, huge killer wave. Okay, back to business. Solar radiation and its characteristics. Energy from the sun. So there are a wide amount of energy is released, right? So the spectrum is huge. I think in the first class we covered the radiation, different wavelength. Is that correct? From UV to IR. I think so. But I don't know. So energy from the sun in the form of UV, visible, infrared, electromagnetic radiation is known as solar radiation. Did I put the topic here? Okay. I think I should have blocked it. Okay. Annual solar radiation on a horizontal surface at the equator is over 2000 kilowatt hour per meter square. In Northern Europe, this falls about 1000 kilowatt hour per annum. And the tilt, that is what I was talking about, the angle of incidence. The tilt between the sun and the land reduces the intensity of the midday of sun. We all agree actually. So these are all the different parameters of energy which you can get through from the class notes. Okay. Solar energy. Okay, this is for, I just want to sum it up. Solar energy originates from the sun, driven by nuclear fusion of hydrogen and helium. Surface temperature is approximately 5,500 degrees Celsius. 5,500 degrees Celsius. Okay. Is there anything comes out in your mind? With respect to, right, we studied a bit of thermodynamics in our second class. Am I right? Right. Is there anything comes to your mind on the surface temperature and the radiance relationship? How it is going to get related to each other? As I mentioned to you in my last class, previous class and the one before, all my classes notes will be related to the 1, 2 and 3 series of classes. It's all related. All the classes will be related. I mentioned to you. So I would appreciate, you know the answer. Surface temperature is approximately 5,500 degrees. How radiance and the surface temperature are related? Yeah, that's a very simple way of telling. Yeah, exactly. It's a logical answer. But you can go much bit more better, specifics. Because we have touched the thermodynamics, right? And these kind of questions will be there in your question paper, in your exams. I won't tell that this is exactly the question I'm going to ask you. Any more?
Are you on about how the heat or
Relations.
dissipates?
Equations or relations which you can tell. How the radiance and solar radiation and temperature are related. In what proportion? Okay, you can say. You said that it increases, right? In what proportion it is increasing?
We're talking about, first of all, thermodynamics.
Perfect. Agree to disagree. That's not. That's not bar. No. Okay. We'll move on. Okay. I'm covering this. Okay. I'm covering this in my class. Solar radiation and characteristics. What did I put here? Heat is transferred from the sun to earth. Right? Heat is transferred from the sun to earth through electromagnetic radiation. Agree? That is what solar radiation is. Nature of electromagnetic radiation depends on temperature and emissivity of the body. Now, one more clue. Nature of electromagnetic radiation. That's an electromagnetic radiation, right? That depends on the emissivity of the body. One more clue. Okay, we'll move on. The quietness is also makes others sleep. Okay, so nature of electromagnetic radiation depends on the temperature and emissivity of the body. Anything anyone wants to say? No? Okay. So this is a spectrum of solar radiation. We again cover. It goes from visible. So UV visible is the maximum visible range, and as you go down, the electromagnetic, it's like the more you closer, the more the radiation you get. More you farther away, less radiation you get. So that's why the curve is it's a Gaussian curve, and sunlight at the top of the atmosphere visible, and it always goes towards. Another clue is started coming, black body spectrum, and then the radiation goes to the sea level with different absorption bands are coming out. With respect to water vapor, it's going to significantly affect the atmosphere at some stage. If you start giving more greenhouse gases, that's one of the reasons why I put CO2, H2O, and all the other things. So that's what I want to explain from that curve. Okay, and the sun produces light with a distribution similar to what would be expected from 5000. You know that 5000 Kelvin I mentioned, the surface temperature. This is equivalent to black body. That's another third clue. Black body, which is approximately the sun's surface temperature. Now, pause it for a minute, or a few minutes. Can you brush your brains? Stefan Boy. No, anymore. Anymore? Okay, I don't want to make other guys sleep as well. Radiation interacts with matter in several ways. I'll come back to you. Okay, you know the answer. Radiation interacts with matter in several ways. What are those several ways? What are all those several ways? Radiation interacts with matter. Any matter. Sorry? Heats it up. What is that called? Term. I need one single term. Okay? There may be 4 or 5. I need only one term. Key. Listen. This is what I'm expecting in your assignments as well. Okay? So the guidelines in the assignment was clear. Like I need that if you use keywords, you will get more points. Right? The keywords. If you use properly the keywords rather than heat, absorb, heat and those things. So I'm looking for specific terms. So those terms you start building it now itself. Thermal. Okay, thermal. What are all how it interacts in several ways? Thermal interaction.
I know with the radiation absorption based on resistivity and it's absorbing into the material.
Go back further. Go back one step. What do you say?
Radiation absorption.
Absorption. That's what I'm looking for. Okay? Absorption. Okay? That's one term. It interacts. It absorbs. Right? So absorption is one term. Radiation interacts with matter and that's key term actually. Absorption. Next. Thermal absorption. Then conduction. Yes or no? Okay. Reflection. Okay, reflection. Huh? Refraction. Refraction. Okay. Refraction.
Diffusion.
Diffusion.
Yeah.
Diffusion.
Yeah.
Did you say diffusion? Okay, diffusion. Absorption, reflection, refraction, diffusion, thermal. Okay. Absorption. So you got the point, man. You got the point. Absorption. Transmission. Do you agree? Transmission interacts in several ways. Absorption. Yeah, you need to transmit, right? The light has to transmit to other surfaces. Absorbed and then transmits to other surfaces. Then next. Any other thing now? Absorption, transmission. Okay. Do you remember a curve, which is the third time I'm putting this? Do you remember a curve? Not a curve, a cartoon, which I put in the very first class or second class. In the first two classes, a cartoon showing that solar radiation is coming, hitting the surface, how much is it getting absorbed, and reflected, transmitted. Do you remember how much percentage? Do you remember that picture, cartoon picture?
The energy budget, yeah.
Energy budget curve, exactly. That energy budget curve, that's is the key parameters. That gives reflectivity and all the other things. Scattering, that's called. Okay? That takes care of both your arguments, reflection and refraction. Okay? Scatters. Absorption, transmission, scattering. One more. Reflection. That's it. Okay? This is how it is. Done. Okay, the incoming solar radiation. Okay, bit more physics. Incoming solar radiation. Okay, what are all these light pockets are called in physics? Photons, exactly. So the incoming photons, I would say solar radiation, photons. So that's getting reflected by the Earth surface, reflected and absorbed by the Earth surfaces, goes there, and then again absorbed on the clouds, and then it again gets reflected and absorbs. Absorption also happens in the water vapor zones, and it scatters the aerosol molecules. This is a cartoon picture. Okay, this is what is happening. These are all the key things happening in either in the form of energy budget that is different. This is talking about how it is going interacting with the surface of the Earth itself. Okay, that's how it is. Any comments? Shall I move on? Okay. Solar radiation and characteristics continues. When a photon is absorbed, its energy is changed into different form, electrical or heat. When a photon is absorbed, its energy is changed into different form, electrical or heat. A fraction of the incoming solar radiation is reflected back into space, which we saw, right? It is known as albedo of the Earth's atmosphere system. Annual average is about 0.35. The reflection from the clouds is 0.2. Reflection of cloudless atmosphere, stratosphere, even called particles and gases, 0.1. And there are different parameters in the radiation absorbed by the Earth atmosphere. Okay. So there are many things happening during this time. Okay. These are all another key things we may need to notice. Direct solar radiation. Somebody talked about diffusion. Okay. That is direct solar radiation. Solar radiation at normal incidence. I am going to show you what is normal incidence and how it is important. Okay. Now, solar radiation at normal incidence in the direct beam from the sun. Diffuse solar radiation, that's scattering the radiation on the horizontal direction. Okay, that also I'm going to show you in the form of cartoons, graphs, and also I'm going to show you in the equations form. Okay, basic equations forms. And global solar radiation, the sum of the direct beam plus the diffused component on a horizontal surface. So somebody said that it has to be some perpendicular, right? That's what you said, perpendicular to the beam. Okay, you will know about why it is. And infrared radiation, terrestrial infrared radiation emitted by the sky on the surface. So net radiation balance is combined downward solar radiation, sky infrared minus upward reflected solar and terrestrial radiations. And turbidity is another thing, measure of the amount of scattering in the atmosphere. So all these are again put together in these key things: absorption, transmission, scattering and reflection. All these things will come here. That's why I say there are all key parameters and key words which you may need to use in your assignments if you are using in the solar. Okay, if you take a combination of solar or wind or whatever it is. Okay. We all agree that solar radiation from the black body, sun is approximated as black body, is related to temperature from huh? Yeah. You are going to lose your laptop. from Stephen Boltzmann law. Guys, do you remember now? Don't roll your eyes. The last thing I want. Are you able to remember? I taught Stephen Boltzmann law in the second class. Can you guys remember the equation approximately? You saw the notes. Now I'm going to kill you. Okay? Anyone? That's a good attempt. I know that. I appreciate it. Okay. Okay. You said radiation related to temperature, right? It increases as a function of temperature. So proportional. How much it is? How many make it? Square. I'm really going to kill you guys. Okay, everyone. Really going to kill you guys. I told specifically, go through your lecture notes. And I think I put, yesterday for the first time, I put a note as well. What are all the topics I will be covering today? You guys have, everyone got that, right? Mail? Yeah, so next class, please revise, okay? G is sigma t power 4. That's what Stephen's Boltzmann law is. Okay? G is the irradiance and sigma is the Boltzmann constant and it's proportional to t power 4. Okay? And the values of T, G is the solar radiation, is in watt per meter square. Okay? Units are critical. Sigma is Stephen's Boltzmann constant, 5.6 into 10 power 18, minus 8 joules per sm square and kil per 4. Okay. I'm now in bad books with some of the people, guys. Calculate the irradiance of the sun at temperature 5500 degrees Celsius at its surface. Okay. I'm not asking you to do the calculation. If you do, that would be good. I don't think I have the answer here. So you do this G is equal to sigma t power 4 and calculate what is the answer is. Okay? That's a puzzle to you. Solar irradiance units is watt per meter square. So this is equivalent to power density, right? Power density. Density, how we are expressing? With some area, right? Some square area. That's why watt per square meter. So that's nothing but power density. So if you integrate the curve, right? You are getting some curve. If you make an equation, naturally you will get some curve, right? X and Y curve. If you integrate that over the time to find the radiation, you can get the energy density. That's joules per square centimeter. These are all very important. It's not just like that I'm putting. These are all important when you're talking about I need to have the solar panel in, let's say, County Mayo, or I'm going to have a solar panel in somewhere in outskirts of Dublin or in Wicklow. What is the energy density you are going to talk about there? What is the power density you are receiving? What type of units you are going to operate? So how we are going to get the variant of the curve? So all these things you need to know. So there is a new term, insolation. Insolation. Insolation is the measure of irradiance whose source is the sun. Have you ever heard of this term, insolation? It's not insulation, it's not a spelling mistake. So don't give a no guys, you're wrong, it's insulation. No, it's not insulation. It's called insolation. It's a measure of irradiance, okay? Measure of amount of irradiation coming to the sun, that's insolation, okay? Irradiance where the source is the sun. Okay? Right. Irradiance will decrease as the distance from the sun increases and is proportional to the square of the distance. So the answer to the first slide, the first question of mine is surface temperature, right? 5000. So if you do proper calculation for this, calculate the irradiation of the sun at temperature, you will end up with this answer. Okay? 6.3 into 10 power minus 7 watt per meter square. Solve the equation, okay? And let me know you are getting the same answer when you can, okay? So let us see. Let us imagine the surface of the sphere. So sun is a sphere, right? Do you agree? Of course you have to agree, there's no other rule. So if you say that, Galileo will come and kill you. So surface of the sphere is pi r square, 4 pi r square, right? And r is the radius of the sphere. Radius of the sun is, okay, I should have asked you, 695,000 kilometers. That's the radius of the sun. Okay, and g, the radius, the irradiance at any distance r from the sun is given by g is equal to g sun, that is into 4 pi r square sun divided by 4 pi r square. Okay, bit of equations. Okay, if we go into visual imagination, you can clearly see what is happening here. That's our sun and the earth. So distance between the sun and the earth. And if you go back to the other equation, then you can relate relative irradiance. Okay, the back reflections coming out from the earth and other parameters you can calculate. And you know that it goes in a somewhat, not exactly, the earth revolves around the sun in a different way, in the conical form. So you know what's happening, the distances are different, so r is different at different positions. Okay, so these are all interesting concepts which you should be including in your assignments, and there will be some questions will be asked in the exams related to that. How the positioning of the sun is going to affect the different irradiation spot. Okay, how it is going to affect, what is the G earth and G sun is. So there are simple equations you should remember. There's no other go. You have to remember these equations, 4 pi r square. It's very simple equations. So there could be something like this. Okay?
The area is also moved as well.
You have to consider this. This is a tilt. Okay? That's a tilt. That is going to happen. Okay? Those are all called solar corrections. We need to include the corrections, the tilt, right? Those tilts you need to include. That is corrections. These are basic concepts. The tilt, that is further again, that is what I said, angle of incidence, right? That angle of incidence is going to vary. Okay. Any other? I agree with you. That's another key issue, key parameter. Okay. I want to give some more life in the class. What day of the year is Earth is closest to Sun in perihelion? So you know what is perihelion, right? You know what is perihelion now, which is closest, right? So what day from here? Can you tell me? I've given a lot of options. I'm not asking you questions here. I give you a lot of options. You tell me. Sorry? 10th of December. He goes for the A. All right. First option.
June 21st.
What is it? What 24th is 21st?
June 21st.
June 21st. B. Yeah. Huh? June 21st. What day of the year Earth is closest to the Sun? That's the question. And June 21st is the one which you gave, right? Okay. Is it June 21st is universal across all the...
No, there's two.
Huh? Is it universal? Or it's only up to Europe? 21st of March. Okay. See, I'm getting some interesting answers. So A, B, D so far.
Is it all depending on where your arm is over to the earth?
No, I don't want to confuse you anymore. The longest day every year, not only. Not longest day, sorry. I'm not taking the longest day. I'm talking about Earth is closest to the Sun.
Longest day is the first. You sure
It
it
doesn't matter where you are.
It doesn't matter, yeah, it doesn't matter. Okay, fine. I agree, it doesn't matter. I just put it in. My question is only Earth closest to Sun, that's it. I'm not asking anything specific. So A, B, D, any more? Come on, guys. Yeah, more options. I've given you G so that at least people can pick and choose. I need you to go quickly. Break the silence.
D.
D. March 21st. I'm not going to ask you why. Okay, don't worry.
Plus spicy.
Okay, D. So he's going for D or G, right? Both. Okay, it could be both. I'm talking about the closest, not farther. Yeah, one is different and another is, it's not equal. It's not equal. If you see my previous diagram, okay, the perihelion and the aphelion is different. Huh? V or E. Okay, he's changing his mind now. V or E again. Go on, go on. I don't know, I have to go to move other slides. Yourself.
I think B, so just I've always known June 21st is the longest day of the year.
Okay. B. So there are a few votes for the B, 2 votes for the D. So B and D are the maximum, right? Any more?
4th of June.
4th of June. We have 4th of June. Oh, that's, yeah. Who said 4th of June? You. Fantastic. I like this. Some different answer. So which is the not picked so far is C and G. G is also picked. So C is the only thing which is odd or not. Nobody has picked C. Can it be C? September the 4th.
Can it? Yeah.
Huh?
It can, but is it?
It can, but it isn't. Okay. I like it. Okay. Break the silence. Slowly coming arrow. It sits in January 4th. E. Okay. Nobody said E. Oh, you said E, is it? Okay. That's where the sun is closest to the earth. Okay? Right. Key parameters involved. We said something, right? Thermal. You said thermal, right? Thermal. What did you say? Somebody said key parameters. Some other.
Time.
Huh? Time, yeah. So irradiation, insolation, right? Direct, diffuse, or direct direction, diffuse or direct. He said diffusion. Okay? And we want to be able to quantify the nature of irradiation on a given surface on the earth. We want to quantify. Can we quantify the nature of solar radiation on a given surface on the earth? Can we quantify? If so, how we can quantify that? Because that will again going into renewable energy. How much energy is needed, consumed? Okay. Corrections. Solar corrections. Okay. That's what you're talking about, the tilt and other things. So, right. This slide, I specifically, usually I don't like to populate the slides like this. Make it shorter points. But there is a reason why we would like to put everything together in one slide. Because this slide is another big picture. It talks about big picture. Okay. So direct normal solar radiation is the part of sunlight that comes directly from the sun. Is the part of sunlight that comes directly from the sun. This would exclude diffuse radiation, such as that which would, through on a cloudy day, indicating the clearness of the sky. Direct normal radiation is the sunlight that comes directly from the sun. This would exclude the diffuse radiation, such as that which on a clear day. That's what I mean, direct sunlight. Okay. Diffuse sky radiation is reaching the solar radiation that is reaching the Earth's surface after being scattered. The scattering take place. So I put the radiation absorption, scattering. So another thing is scattering is coming here. Scattered from the direct solar beam by molecules and suspensions, which I said in the other slide. Like clouds will be there, you will get scattering takes place in the molecules around the water vapor happening. So So that is also diffuse sky radiation. Okay. So direct solar beam by molecules, suspenoids in the atmosphere. It is also called skylight, diffuse skylight, sky radiation, and is the reason for the changes in the color of the sky. Is the scattering. So scattering takes place in different angles and different positions. Okay. For the total light removed from the direct solar beam by scattering in the Earth atmosphere, it's approximately around 25% of the incident solar radiation when the sun is high on the sky, depending on the amount of dust and the haze in the atmosphere. About 2/3 ultimately reaches the Earth's diffuse radiation. Global horizontal radiation. What is global horizontal radiation? That's another new term. So you can read it. What is that? I can read it, but I'm going to ask you some questions on that.
Is that the radiation that's reflected back off the Earth's surface? It's absorbed and it's thrown back up through.
It's a direct reflection from the Earth to Sun. Is that what you mean?
You know where the radiation hits the Earth's surface, there's a certain amount of reflection back out into space. I presume it's related to that.
Global horizontal radiation. Okay, we'll see. So I'll read it out, then we can go for the examples like what you are saying. Total radiation, sum of direct, diffuse, ground reflected radiation. That's what it is, right? But sum of direct and diffuse. What is diffuse here? That you need to tell me, okay? This is again coming into the energy budget curve. I merely put the diffusion in. Diffuse and reflected radiation. However, because ground reflected radiation is usually insignificant compared to the direct and diffuse, for all practical purposes, global radiation is said to be sum of direct and diffused radiation only. Okay, global radiation is sum of direct and diffused radiation. What is diffused radiation? Give examples of what you think of diffused radiation. Because I want to get this in your head now.
Change of direction.
Sorry?
Change of direction.
What is diffusion? You cannot say that change of direction, that's scattering. What is diffusion? What is diffusing one on another?
Separating the light.
Sorry?
The separating of light.
Separating of it. That's again scattering. What is scattering? Scatter.
Bending on different directions. Diffusion would be separating the individual parts of it.
Diffuse. What is diffuse?
Spreading evenly.
Sorry?
Spreading evenly.
Spreading evenly.
Well, not spreading from there.
What is absorption and what is diffusion?
I think diffusion is like it moves from a higher concentration, to those of lower concentrated areas.
You mean the density, different density?
No, the scattering.
What is concentration? You mean what concentration?
Concentration means you spread a powder like it diffuses from.
Okay, I am shining a light now.
Yeah.
I have a solar light here in my hand. Okay, and you tell me now. I'm going to switch it on. Okay, how? What do you mean by this? By the concentration and scattering? I don't understand. You tell me. I have a solar light here. I'm going to flash it on.
Concentration is when you focus in the beam.
Diffusion, right?
Diffusion is when you separate.
Separate, and the intensity is less. Right?
Does not scatter.
Sorry?
Is that not a form of scattering?
Yeah, but there are two ways of scattering. The scattering which we are talking about here is the light is when I put the scattering on the top. What is scattering? How the light is scattered and forms the different colors on the surface, right? On the clouds, why the cloud is different? That's due to different scattering. It's not due to diffusion. This is also the form of diffusion. But diffusion is again decrease in the intensities of the light because of different effects, surface effects. So the sum of decreased intensity and the direct intensity and a critical part in the global horizontal radiation. So these global horizontal radiation will be key in determining the temperature and also coming back to our Boltzmann equation. So it will vary. You have, say for example, if I put some temperature on T is equal to 200 Kelvin or 100 Kelvin, what is happening to the irradiance as compared to the sun? If I ask you this question, you would be able to position to answer this. You will be in a position to able to understand what I am talking. Are you with me?
Could you just repeat that last point?
Repeat last point. Okay, repeat. Okay, if I ask you a question, like say in the flat surface or in some other surfaces, T is equal to 100 Kelvin. Okay, calculate the irradiance with respect to sun. Then again, you will go into Stephen Boltzmann. T is equal to sigma T power 4. You know what is T in the Earth's sun surface temperature? 5000 degrees, some 5000 degrees Celsius. And you know, I will give you the temperature of whatever temperature it is I want to give. Calculate the irradiance with respect to sun. Okay? So I may ask you this kind of question. This is important, crucial. This is important and crucial when you are talking about you or somebody told about the materials. It depends on the material properties. And again, choosing the materials is also key. How much irradiance it can accumulate. Okay? And when some people are going to do solar thermal, they need to also understand the same thing. How much radius is going to reflect at what angle. Okay? So, insolation is another key term which we are discussing. Is the measure of the solar radiation energy received on a given surface area in a given time. Okay? It is commonly expressed as average irradiance in watts per square meter per day. And I don't want to introduce this new term until you are familiar, but I can just start introducing. In case of photovoltaic, is commonly measured as kilowatt hour and kilowatts. Photovoltaic. What is photovoltaic? I know that you all know for photovoltaics, okay? What is photovoltaic? Can you say from the word itself? I don't want one huge explanation now. Photo, get the voltage.
Yeah.
That's it. Photo and voltaic married together. That's it. Get current and electricity, photons from photons. That's it. Very simple. Right. Direct normal irradiation, direct normal radiation. So, guys, scattering radiation, ozone, irradiation at some specific points, watts. It's a mixture of everything. Rayleigh scattering by molecules in air, which we have been discussing about the scattering happening in the atmosphere, absorbance by ozone, and absorption by uniformly mixing gases, greenhouse gases, CO2 and O2, water vapor absorption, extinction of aerosol particles, and extinction by high clouds and cirrus types, and scattering and absorption are strongly dependent, wavelength dependent. Scattering and absorption are strongly wavelength dependent. What are the consequences of this? Concentrate on this. This is particular equation, the direct normal radiation that depends on Rayleigh scattering by air molecules in the air, by the molecules in the air, absorption of the ozone, we know ozone layer there, and absorption by universally mixed gases, we know the greenhouse gases, we studied CO2 and other O2s, absorption of water vapor, aerosol particles, and high clouds. So all these scattering and absorption will be taking place and are strongly wavelength dependent. What are the consequences of this?
A certain wavelength gets through, whether it be long, short, or medium wave. As a consequence of that impacts the amount of energy, that's the amount of energy that's available for absorption by the body into the.
Sure, I agree with you. It's a good try. It's a fantastic try. Okay. Okay, I will try to bit more, some more specific answer from you guys, okay? So can you relate this to variation of temperature and pressure? Okay, scattering absorption are strongly dependent. Consequence is, I agree with your answer. That is the exact answer I'm looking for, but in a bit more, yeah. Think about it. We'll get back after the break as well. Okay. Cloud free. Okay, I'm going to come back to that answer. I'm not going to forget it. Okay. Cloud free, direct beam insolation and cloudy periods prevailing or diffuse irradiation and average to mean irradiance. Cloud free and cloudy periods average to mean irradiance. Okay. For the assessment of solar power plant sites, short interval recordings of sunshine, direct and diffuse radiation are required. That's perfect, because you don't need to have you need to have both direct and diffuse radiation in order to avoid a lot of hot spots, thermal heating, localized heating on the surfaces. So for the assessment of solar power plants, a short interval recordings of sunshine is required. Clouds can be classified by their optical depth. It's a new term, optical depth, and I will be talking about this class, next class, and I'm thinking of at least 3 classes for solar radiation. And next class we will be touching slowly on the photovoltaic 1 and 2. That's what I was thinking of. Okay, so cloud-free line of sight probabilities are available in the World Atlas. Indicates for a given time and location what percentage of the sky is cloud-free. Okay, this is important for projects. People who are doing it on solar, please refer to this. And then also indicate it will also gives you the time and location and the sky when it is cloud free. So you can also refer one more thing. I think I forgot to put the reference here. Go back to the Energy Lab website that gives the entire cost economic factors. One of the guys did a good job in the project. He made a cost analysis talking about different areas of that, how much energy is received, and how much cost involved, and what is the economics involved, and what is the efficiency you can get. So he made a rough calculation, so you can always take this as a starting point. It's software, you can type whatever the latitude and longitude, you get everything. Okay, so you can also take from there, and you can use this as a starting point as well. So I'll go for another 5 minutes, then take a break. European, after this I'm going to take a break. Okay, European radiation. Okay, the European Commission Joint Research Center. Please visit this website. This has more information. Talks about solar, and this is more talks about the Europe. How much photovoltaic solar electricity potential going across the Europe. Okay, how much energy is getting released in terms of global irradiation. Photovoltaic modules with the different types of emissivities. As you can say, different emission varies from here to here. So we are much more greener, as you know that. We are getting around 1,200, 1,300 hours of sunshine or something like that. So whereas the other parts of Africa are getting more. So we need to understand the complexities involved and the key parameters involved in this. So I just want to give you a flavor of this, and then we will take a break now. Okay, now I need to know how to stop this. Alright, welcome back, guys. I shouldn't have said it worked again. Okay, back to square one. Right. Resume. Okay. I hope it works. Yeah, it is working. Okay. So before the class, we were talking about how much radiation which we are receiving from the sun across northern Europe, and we will be go much specific details from the quotation from met.ie. You can get these results. So Ireland normally gets between 1400 to 1700 hours of sunshine each year, and the Eastern Sahara Desert, which we are talking, which is the sunniest place in the globe, gets an average of about 300 hours per year. And Irish skies are completely covered by clouds. No wonder why. Over 50% of the time, this is due to geographical positioning of the northwest of Europe, close to the path of Atlantic low pressure systems, which tends to keep us in humid, cloudy air flows for much of the time. So, this is an important data which I took it from the Stephen Daniels 2009 lecture series. So, in 1887 was the sunniest summer in the 100 years of Irish history, from 1881 to 1980, according to the measurements made at Phoenix Park in Dublin. The more recent, 1980, was the dullest period as well. So yeah, 1887 was the sunniest summer. So I don't know what temperature they are talking about. Anyone knows? Or anyone heard about this before?
32 degrees Celsius.
Is it 32 degrees? Oh, as warm as it goes. Okay. I'm originally from the southern part of India called Chennai. The average temperature is 32. The sunniest part there is the hottest summer in that part of the region is close to around 45 degrees. It came somewhere around 48 degrees. I think it reached mercury. That was about 70 years ago. So it's similar. So the difference in that brings out the positioning of the globe, the rotation, the optic axis is changing. So all these things will come into picture. Okay, and the difference is considerable with 1887 being twice as sunny as that of 1980. So this is sort of it's not as important data, but if you think of the positioning of the sun with respect to the earth, the latitude of what is the latitude and longitude of African countries, and also Sahara Desert, why it is happening, and say you can also do some sort of a basic calculations with respect to the radiation with respect to the sun, and then the angle, and considering the perihelion and aphelion, what is the positioning, how much sun rays will come and hit Sahara Desert at what is the maximum temperature it will go at what time. You can always calculate from the Stephen's Boltzmann law. So that is why it is very critical. I think I mentioned that in my first class itself, second class itself, right? Can we move on from this? I think so, yeah. So typical figures. The intensity of the sunlight that reaches the earth varies with time. So somebody mentioned time. That's correct. With respect to time of the day and the year and the location. We talked about location, weather conditions, which we didn't speak. Again, it is the effect of atmosphere comes into picture. So the time, day of the year, location, weather conditions. The total energy on a daily basis and annual basis is called irradiation that we discussed. Irradiation, and the measure of irradiation is what? Measure of irradiation is what? What? That's measure of irradiation. What? Joules. I introduced a new term. He is after Stephen Hawking. I introduced a new term today. Guys, you are killing me today. aren't you? Okay, go back. I think it was there. Measure of solar radiation energy received on a given surface area in time. What is that called? What is that called? Insolation. I think I gave it too longer a break, I think. That's why I'm in trouble. Okay. So the intensity of the sunlight, so insolation is also a critical factor. Okay. So here the total energy on a daily basis or annual basis is called irradiation and indicates the strength of the sunshine. Irradiation is expressed in watt-hour per meter square. So you're all right in telling that units, but I wasn't looking for that. I explain you now. To simplify the calculation with irradiation data, solar energy is expressed equivalence of hours. Bright sunlight corresponds to power of about 1000 watt-hour, as you said, 1000 watt-hour, and corresponds to an amount of 1 kilowatt-hour per meter square. This is approximately the solar energy when the sun shines on a cloudless day. Oh, I can't say that. Cloudless day today in the summer or on a surface of 1 square meter. Okay. The optimal orientation and inclination angle varies from site to site. What does it mean? The optimum orientation and inclination angle. What is inclination angle? Any ideas, thoughts? Okay, read it again. Okay, the optimal orientation. I'm talking about the orientation and inclination angle. What is orientation? What is inclination angle? There are two things that are happening here. Okay.
So one is the orientation is when it can't go and sit there, the inclination when it goes up. Right.
Okay, I can take that. Optimum orientation and inclination angle will vary from site to site. So, will it vary? Will it have a much effect in Sahara Desert?
Yes.
Why?
Because the way the Earth is tilted, the angles will be different to where it originates or any other part of the world. It all depends on what way the tilt is.
Okay, say in a country like Ireland, the sun hours is about 1500, right? Whereas in a country like in Sahara Desert or in Arabian countries, it's about 4000, so it's 4 times more. Okay, and I would expect 4 times intense as well. So compared to the not 4 times, 2 times intense as well. Okay, so now we have to talk intense in the sense we are talking about the radiance, right? Are you with me?
Yeah.
So when you are comparing the radiance with respect to Ireland and with respect to Sahara Desert, okay? So we are talking about the ratio of the radiance, say G, Ireland with respect to sun, G Sahara Desert with respect to G sun. Okay, so this ratio is the one which is going to corresponds to defining what is the optimum angle at which the rays are hitting more. Okay, and this will be also corresponds to what we are talking about, the different problems which we are having, like localized heating effect. It will be more there and compared here, and the cell efficiency will go down. So the optimal angle on both sides, if you have a flat surface, that we are talking about orientation of the surface and also the orientation of the sun. So you need to get the combination right, whether you are going for either for solar thermal or photovoltaic. Are you with me? Is everyone okay? Right. So that's what I mean. That's a critical parameter to be considered. Okay? And your exam questions will also be based under this. I won't say what it is because I don't know. Based on this, in comparison with the perihelion and the perihelion as well, it will be there. Okay? So, and also Boltzmann, there are lots of other factors in thermodynamics, including the isotherm and adiabatic, or everything put together. So it will be like a good package. How the technology is going to, we are looking for, what efficiency we will be looking for, what model we are going to see. So it's all combination of many things. Okay? Ideally, you want the cell orientation at 90 degrees, right? That's what 90 degrees to the sun at all the times. So you get maximum efficiency. Okay? That's the typical figures.
What about if you're using parabolic dish?
Sorry?
What if you're using a parabolic dish?
That's what people have been using, right? For solar concentrators. Sorry, I didn't get
It
it.
doesn't matter if it's focused in.
Sorry?
The angle is always focused to a focus point.
Focal point, yeah. It will be focused. It will be, the angle will be, you can also tilt it according to the intensity. Am I answering your question? Yeah. Okay. Angle of incidence is critical. That's what we have been talking a few minutes back. Okay. So A receives, in the figure I am putting, it's a flat surface. What we are talking about, the orientation. So I am making sure that I am hitting the sun directly on top of the surface. Okay. So it receives, A receives all radiation. Now I am tilting it. B receives some, right? And D receives none. Okay. So computing G on normal surfaces, theta is the angle of incidence in degrees, and GT is a new term again. If you go, what is cosine? Sorry guys, I have to talk some geometry here. What is cosine of the angle? What is cosine? Cos. Sorry? Adjacent over hypotenuse. Is that what you said? Do you all agree? Or it's adjacent by hypotenuse or some other thing? He's laughing now. That's cos theta, right? Okay. So GT is equal to G cos theta, and GT is the tilt irradiance. So that's how we are going to compute. Okay? And if you go to the irradiance, G is the sun, and then we can always compare with respect to different tilt as well. So that's what I want to say about this. And before I go to next slide, are you guys all familiar with zenith angle? Zeta? Right, okay. Okay, if I tilt, the angle of incidence again critical. If I tilt the surface, say that beta is the surface, if theta is equal to beta, GT is equal to G cos theta. So that is the tilted surface. So you have a surface normal here. This is the normal to the surface, and the irradiance is coming in. And then if you start computing, what is how much irradiance corresponds to a tilt? So it is given by GT is equal to GT G cos theta. Okay. So imagine a situation if the surface is horizontal, and you are going into the other situation. The surface is horizontal, and the angle of irradiance. So we are talking about different positions, right, of the sun now. So irradiance and an angle. The angle between the sun and the horizontal surface, it is important to consider the zenith angle. That's theta, is it? This is very, very, very important when compared to when you are calculating the different effects of irradiance, thermal losses as well. And the zenith angle is the angle of incidence for a horizontal surface, right? And I'm extremely sorry, there are two more pictures which I used in the Mac is missing here. Okay, I put two more pictures here, so I don't know what happened. So probably I should be consistent with the Windows. So when I upload the file, I have to correct it. Okay. Okay, it's coming now. I didn't put this. I didn't put the animation. I didn't animate this at all. Okay, so that's this. Say for example, if you have a surface normal, the theta is that when the sun is shining, we have an angle of inclination. When the shine is up there, exactly theta z is equal to 0. So that's what I want to mention. So we have a different inclination, and then you have to compute it according to the different angle of incidence. So angle of incidence, it is key parameter. Zenith angle is key parameter. GEZ is very key, and G tilt is also key parameter. So all these are key factors which will affect the irradiance corresponds to the suns. Okay. So when you compare without tilt and with tilt, without tilt G0, GO, on cos Z without tilt, and if I tilt it, I say that GOT, whatever we want to call, okay, and GON cos theta without tilt, with tilt. Okay, solar panel tilt angle. So sun moves across the sky from east to west, so everyone knows. So solar panels are more effective in their position facing the sun at a perpendicular angle at the noon. Okay, solar panels are usually placed on a roof or a frame and have a fixed position and cannot follow the movement of the sun along the sky. Therefore, they will not face the sun with an optimal 90 degrees angle all the time. We know that. Okay, it cannot be tilted. The angle between the horizontal plane and the solar panel is called tilt angle, which is already explained in the previous slides. What is tilt angle is, right? So these parameters are critical in defining the efficiency and consistency of the solar cells and the solar panels. So due to the motion of the earth around the sun, there are also seasonal variations. In the winter, the sun will not reach the same angle as in summer. Right? So that's again the effect of atmosphere. And ideally in the summer, solar panels should be placed somewhat more horizontal to benefit most of the sun high in the sky. However, these panels will not be placed optimally for the winter in the sun. So there are reasons because of the different angle of inclination hitting the rays. So that is why I am trying to bring the concept angle of inclination and theta, the zenith angle, are critical parameters in defining the efficiency of the cell. So that's what these 2 points are coherently achieving. To achieve the best year-round performance, solar panels should be installed at a fixed angle, which lies somewhat between optimal angle between summer and the winter. We agree. And for each latitude, there is an optimum tilt angle. So we know this point, right? When you do the calculations and the modeling, you need to be familiar with this. For each latitude, there is an optimum tilt angle. So whoever does their assignments on this, I would like to see what is the tilt angle if you're comparing with any international standards. I would like to see, you have to give an explanation with respect to tilt angle and how much sun is, how much solar radiation, G, Z will be there, and that corresponds to how we are going to compare that G, Z with respect to G of Ireland. Okay? Or even you can compare with Germany and Ireland, I don't mind, with international standards. For Germany and Ireland, who is the best leaders for how much irradiation they are using and how much we are using. So we need comparison. For that you need to get the optimal tilt angle. And you can even play with the tilt angle. Like, see, they are using between halfway between summer and winter. We can use quarters of that. Whatever it is, we have to give a proper justification. Okay? And also the cost benefits regarding that will also be there. Okay.
Would you not be best having that the solar cell moving throughout the day?
Sorry?
Would you not be better off being able to adjust it throughout the day?
There are other complications involved if you start thinking of moving it, right? So the complication is differential cooling. Okay, you have to have a differential cooling panel, and other losses will be there. Like, how are you going to compensate for different thermal losses? Like, say for example, if you have started tilting again, right? That's again the differential temperature will be there, but you don't know those differential temperature. But you can predict the differential temperature when it sits. You know the gradient, how it is going to fall. Either it's going to fall logarithmically or linearly. Okay, when you start moving, you are disturbing too many parameters, and all the mechanical noises, electrical noises components, you need to really take care of account. So that's another critical problem. Are you with me?
Yes.
Yeah. So where we are, okay. Only near to the equator, solar panels should be placed horizontally. Do you agree? No. Wow. Only near to the equator, solar panels should be placed horizontally. No. The answer is no. Is it?
Not horizontally, there should be still a slight tilt on it though. But it's not completely on a. It's on a.
On the equator?
Yeah, it's a tilted axis the Earth's on, so the equator might still have an angle together. Wouldn't it?
Still preparation of the globe back and forth. Like, it doesn't spin perfectly on the north and south.
Exactly.
Or to sort that out
It goes back and forth.
But if it's horizontal, like, you know, the sun's not going to be. The sun's going to be here, like the tilt of the Earth is slightly.
What is horizontal? You're talking about vertical. That is vertical. You're showing me vertical.
No, I'm showing you the tilt of the Earth. So
Tilt of the Earth. You're talking about the Earth, okay?
So if you have a horizontal to there, you know it's going to be facing out this direction, where the sun will be a little bit off.
Are we talking about optimum tilt, or you're talking about the perfect one? I am here talking about optimum tilt angle, right? So where you get the maximum efficiency. Okay, if we start tilting more, or if you have a tilt, will I get a maximum efficiency? No? Think about it. Think about it. Okay? Usually I will give the answer with the red line, but I'm just going to go on. Okay. Tilt. Tilt in the azimuthal angle of a photovoltaic cell. So I will be introducing photovoltaic module in few slides. Right? So this is for specifically giving you the flavor, but this is not a photovoltaic class immediately. The photovoltaic class will be there next week. Okay? What is photovoltaic and what are the things, necessary things will be there, need to fill the gap, all these things will be there. But I just want to give you the thing. The proper tilt in the azimuthal angle choice is by far more important for photovoltaic systems designed for that than the solar thermal systems. Okay? So the manual or automatic angle adjustments can increase the total light electricity conversion up to 30% and more in locations with high values of solar radiation. The incident angle should be close to 90 degrees as possible. Shaded locations, including partially shaded, are not suitable for photovoltaic module fixation. Module should be south oriented. Okay. The following are general recommendations should be considered if you design a photovoltaic system. Yearly average maximum output power. The photovoltaic modules tilt angle should be equal to local latitude. Now you got it? Tilt angle should be equal to local latitude to get maximum efficiency. So what is the tilt angle for Ireland? No worry, I'm not looking for answer. Definitely, this is not an assumption. This is something serious. We need to work it out. So photovoltaic tilt angles and should be equal to local latitude. So what is the latitude you have? Again, it's all boiled down to the same GT, GH, cos theta. So you need to know this. So maximum output power in winter. The photovoltaic module tilt angle should be equal local latitude plus 15 degrees, maximum 20 degrees. Such a tilt angle is good solution in areas where winter load is greater than in summer load. So this is particularly efficient compared to Scandinavian countries and also Ireland and the parts of England and Scotland as well. Okay, so this statement is particularly for us. So the photovoltaic should be an angle should be equal to local latitude. Such a tilt angle in good solution where the winter load is greater than summer. Electricity consumption for lighting is greater during the winter than summer. We know all this general statement. That's why we need to have maximum efficiency. The manual photovoltaic module tilt angle adjustment is another key parameter. In small systems, modules should be fixed in a way which allows manual adjustments of the module tilt angle. Okay? And in March, the tilt angle should be adjusted equal to latitude. In May, tilt angle equals latitude minus 10 degrees. September, so its complete adjustments can be done. With such adjustments, the maximum efficiency could be obtained throughout the year. Okay? That's what the question which you are asking, right? But sorry?
That's your angle of declaration.
Declaration, yeah, declination. Okay, so again, the angle of inclination is the key. The angle of declination is the key. So that there will be some parts I will be touching it next class. Some bit of optics and bit of engineering will be there. Okay. What peak? A solar cell produces electricity when it is exposed to light. We know that photovoltaic. Depending on the intensity of the light, irradiance in watt per meter square, a solar cell produces more or less electricity. Bright sunlight is preferable to shade, and the shade is better than electric light. To compare solar cells and the panels, it is necessary to know the so-called nominal power of such a cell or a panel. The rated power expressed in watt peak is a measure how much energy such a solar panel can produce under optimal conditions. That's another critical parameter. To compare the solar cells and the panel, it is necessary to know the nominal power output of such a panel. The rated power expressed in watt peak is a measure of how much energy such a panel can produce with the nominal under optimal conditions. What are our optimal conditions? Sorry, can you be more louder? Sorry.
The angle is correct.
Angle. And then you have discussed a few minutes back about the
Perpendicular to
sorry, perpendicular?
cells.
Yeah. That's angle again, right?
Yeah.
Yeah. Okay. Now optimal conditions. Go back, guys.
Cloud cover, no cloud cover.
Atmospheric conditions, right? Transmission, absorption, scattering, and then the angle of the another new parameter, right? So those are all the optimal conditions which we are looking for. How much going to absorb, how much going to scatter, right? Are you with me? Yeah. So those are all the critical parameters. Optimal. That is what I want to say. The solar reference spectrum AM 1.5. This defines the type and color of the light. What is AM 1.5? Anyone knows? Anyone here? It's a new term. I just want to push it forward. AM 1.5. I'm going to talk about this. I'm going to tell you what it is in this class.
The direct distance from the sun.
Sorry?
It's like the relative distance from the sun. The earth to the sun.
What is it?
The distance from the earth to the sun.
Air to the sun.
The earth.
Earth to the sun. Okay.
Does N stand for modulation?
Yeah, amplitude modulation.
No. Okay. Atmospheric effects. Now, there is one of the clue.
What was that?
Atmospheric effect. One of the clue. AM. Make a wild guess. You may get it right. It's not modulation, amplitude modulation or frequency modulation. There is something there which have been talking in terms of energy. Something there when it comes to energy, what is that M belongs? Yeah, you're right. What do you say?
Mass.
Yeah, it's mass. M is stands for mass. A. Atmospheric. Sorry? Air mass. It's an air mass ratio. Okay? That's what is AM. I will explain you what is that. Okay? Air mass ratio. That's what 1.5. That defines the type and the color of the light. Okay? I'll tell you what it is. The cell temperature of 25 degrees. Importantly, the efficiency of a solar panel drops when the cell temperature rises. I think we covered this first class, didn't we? And we justified why Ireland has to go for solar cells more. The more the harder doesn't mean that you get more efficiency. Right? Did we cover it or not? Did we touch it? Sorry? Yeah. So that's again, it's an important that the efficiency of the solar drops when the cell temperature rises. That is the reason for this. More hot spots are created, more radiation. So it's again boiled down to more material properties. It's again, you can influence your Stephens Boltzmann law and then your G cos theta ratio, optimal angle. All these conditions could be used in determining your assignments. Exam questions will be also based on this. There are quite a few things can be done in this. Air mass. Okay, this is what. So effect of absorption depends on the mass of the air, the radiation that travels through. Okay, that's the effects of absorption depends on the mass of the air. So humid conditions. area, humid conditions, mass of the air and the radiation travels, and also you can talk about the stratosphere as well. There are different things. The mass of the air that the solar radiation travels before reaching the surface of the earth varies with the zenith angle, right? The mass of air that solar radiations travel before reaching the surface varies with the zenith angle. Okay, the mass is smallest at solar noon with the sun directly overhead. So in this case, right here, say for example there are differential times it reaches. So P and B, here C. So this is the theta. So this is in the March. It's directly in line. We saw that March 21st, right? When the sun is and the what is that called? It's in the plane. So if we tilt that C in July, so we have an angle here. That's a zenith angle. So that defines the air mass ratio as well. So the air mass is, if you put PC by PB, PC divided by PB, right? The angle. So PC by PB, then for theta greater than 70 degrees, air mass is 1 over cos theta Z, and AM0 is the top of the atmosphere, and AMG is equal to 1.5 degrees, theta Z is 48 degrees. That is the industrial standard. Corresponds to G is equal to 1000 watt. That's what we are discussing. 1000 watt of radiation we are getting in the watt hour per meter square. So at this irradiance, we have air mass ratio AMG is 1.5. That's why it is the standard. Okay, so they calculated universally with respect to corresponding G. So that's what air mass ratio. Okay. So in order to know the air mass ratio, we know the optimal conditions. So now I am in a position to do some site analysis. I know the optimal conditions, what is required, absorption and the air mass ratio. I know the tilt, I know the emissivity, I know the scattering, all these things. I need to do the site analysis. For site analysis, the choice of proper location is the first and very essential step in solar system design procedure. It is critical that the modules are exposed to sunlight without shadowing, at least from 9 AM to 3 PM, okay, to get maximum sunlight. Therefore, the properties and the values of solar insolation should be studied. The modules have to be fixed with a proper tilt angle, allowing the system to have efficient operation. So these are all necessary conditions for the site analysis when you are doing in your assignments. Then planning a solar array installation, one of the first things you will need to determine is the design month. When are you going to put this? Which is the month with the lowest insolation? That's a key parameters. This assumes power consumption is more or less constant throughout the year. If not the case, then design a month. These are all the things people, when you are doing your assignments on the solar or solar hybrid, you should consider. If not the case, that the design month becomes the month with highest average daily power use. In systems tied to an electric grid, that this is not an important because your utility can pick up the slack. But when dealing with off-grid systems, it becomes imperative in order to keep the battery charged. So how we are going to do this? These are all critical parameters when you are going for the solar projects and solar combination with wind or with conventional things. So this point is very critical when you are going with a backup system, or if you have a slack, or if you start thinking of off-grid and on-grid activities. Okay.
What's your maximum power that you're going to generate from solar panels in the summer?
Yeah, summer or whenever you are optimum month, calendar year, yeah.
Maximum consumption of electrical energy will be set.
In the winter. So how we are going to store the energy within the grid, or how the transmission is very, very key. Storage and transmission is the key, right? So how are you going to do? Are you going to use battery to store? You don't know, or any some other novel methods to store. Are you okay? Useful solar power. Solar thermal, direct heating of buildings and water, right? That's what solar thermal is, right? We covered that. And solar photovoltaic, we know that the direct generation of electricity through photons, and you shine photons, and photoelectric effect takes place, and get the energy out of it in a simple physics, simple layman language. Solar biomass, again photosynthesis comes into picture using trees, bacteria, algae, corn, soybeans. There are plenty of things we can do for solar biomass. Is anyone doing solar biomass project? I have not seen actually. Is anyone doing biomass or photosynthesis? No? Okay. So using trees, bacteria, algae. So there are lots of things, like you can also use microbial bacteria, microbial fuel cells, and chemicals, building material, food, feeding plants, humans and other animals. So lots of things that solar is needed, even for the tidal waves. So global averages, the average annual global radiation impinging on a horizontal surface, which amounts approximately 1000 kilowatt hour per meter square in Central Europe, Central Asia and Canada. Kerala reaches approximately 1700 kilowatt per hour in the Mediterranean, 2.2 in equatorial like Africa, Oriental and Australian deserts. In general, seasonal and geographical differences in irradiation are considerable, must be taken into all solar energy applications. We know that seasonal geographical differences, optimal temperatures, optimal tilt angle, it's all very, very important. Key parameters and key languages, key words to be used in considering the efficiency of the solar energy for many applications. Calculations. From European irradiation data, which we showed in the slide 10, Ireland has an average of 1000 kilowatt hours per meter square per year in the slide. Sunlight is equal to 2.7 kilowatt hours per meter square per day, which is 100 watts per meter square. Assume the average total energy consumption in Ireland is 120 kilowatt hour per day per person. So you can get this in the, again, some of the things are missing. I don't know if I click with it coming. No man, I think I'm missing the data here. So that after this there should be something there. Okay, the average total energy consumption is this thing, so you can get it from the wiki. So the population of Ireland is 4 million, is it? 4 million. Assume the panels are 10% efficient. That's slightly, the current efficiency is about 17% for the silicon solar cell. So assuming that we are going for a 10% efficiency, this works out at 440, that is 1 meter square panel per person. Assume approximately 4 times this area per panel needs for the infrastructure. It's about around 177 square meters. Required area for the population of Ireland is around 7,000 square kilometers. Okay, and the area of say County Mayo is about 5,000, and area of Cork is 7,000. So we are very much well located, right? Considering these data, you can go into solar with 10% efficiencies to feed the people. Okay, so that's the moral of the story. Is every situation needs their own thing. Country scale problem needs country scale solution, right? It cannot be universally applicable. We all know country scale problem needs country solution. Economically harvestable power limited. As you know, you guys just talked about, in winter we won't get much sun. At one particular period we get sun. How the storage is going to do, how we are going to harvest those power is very critical. Again, the harvesting power is limited. Storage needed due to fluctuation of nature scale, that is we know, which we are talked about now. Storage needs due to fluctuation nature. So are you going to do combination of solar and wind? Can you use the wind transmission to store the solar energy? Which I don't know. Answer. Can we do that? If not, why we cannot? Or if so, why we can? So those kind of things which we can think of. Infrastructure requirements, substantial it is, and impact of efficiency is also substantial, and these two are really critical as well. Infrastructure requirements are substantial, impact of efficiency is substantial. So these two, how we are going to balance this? The cost benefits comes into the picture on the last two, infrastructure requirements and impact of efficiency. Those two are, sorry.
Okay, so you can, an example of that would be combining solar and geothermal.
Could be. We are talking about in particular to Ireland case. Yeah? Are you?
Yes.
Yeah, that's what I want to answer. Okay, yeah, it could be. What about seasonal variations? That's another critical. Seasonal variations for Ireland. You can see how it varies from day to day. So I can't say seasonal variation, summer, winter. So you get everything in one day. So that's another seasonal variation. So these are all some of the key factors affecting your solar. Okay? I think I'm pretty much come to the end of my slide. Okay, I just want to finish off with another classroom. Okay, you want coal? You want the mines. Big oil problem, right? The oil crisis. You want oil and gas? No, I want solar. You own the wells. So the guys in the Africa, Alaska, and Iraq, Iran, all these guys, oil wells. Okay. Now we want to go to nuclear energy. The guy is down. No, I don't want. He's not thinking. So because you are going to own uranium, and uranium is also decreasing. So no, if you want solar, what do you have to own? You have to own the earth. You don't need to own. You don't need to fight for oil. You don't need to fight for coal. You don't need anything. All you need is the sun. So you own the earth. The solar power is not feasible. Is it feasible or isn't it feasible? That's a question I want to open. Okay? Is the solar power is the feasible one? If so, what is the innovation has to be done? Cost benefits, all the things put together. That's the title, Renewable Energy Technology Economics and Systems. So, solar power, isn't it feasible or is it feasible? That's the question. Okay? Let us see our current alternative fuel plan. Ethanol takes as much energy as we produce. So again, it's a US energy carbon which I picked it up. So whereas our new alternative fuel plan, hydrogen. So go from ethanol to hydrogen, and then this plan doesn't make any sense. Maybe not. That's one of the guy arguing. But you can realize how much energy went in producing it. So I could produce an alternative plan. Still people are still struggling. It isn't a naive technology still. Still people are struggling. It's a niche technology. People are struggling to find optimum. So if you can provide your assignments in very clear and subtle way, that plan it in such a way that covering all the key components, then it is a good project and a good problem to choose. Are you with me? I think I'm done, guys. Thank you so much. Thank you. Any questions or comments, you are always welcome.